Okay, let's look at the history of melting again. We looked at one or two curves already. This is again from the GRACE satellite data, which estimates mass loss in gigatons, and we will look at the water equivalent or sea level rise associated with that. This is the average mass loss of 281 gigatons per year. And remember, about 360 gigatons results in 1 millimeter global sea level rise. And Greenland, you can see, has a very nice seasonal cycle in the ups and downs of the glacier mass. So there is a trend, but there is obviously a seasonal cycle. So there is winter accumulation even as losses are happening. And you can see the pattern of loss is similar to what we saw before, obviously. Both are based on data. So the losses are accelerating over some of these edges where marine effects and the slide down the latitude, altitude, accelerate the glacial melting. So if there is a marine ice sheet instability and there is a carving off and the glacier accelerates downward, then it actually slides down to a lower height where the temperatures are warmer, so the melting can accelerate, and you can see some of those effects happening here on the edges. In the center there is still some small positive mass accumulation, so there is still little places where some net mass gain is happening, but overall it's bad news, and the slope is not linear, so there is a little bit of an acceleration that one can see. People can argue, just statistically speaking, that this time series is not long enough. It could be part of the secular variability where there is a decadal change of mass loss and then potentially increased mass gain. But this is like fingerprinting. You have to look at all the other evidences: ocean warming, atmosphere warming, extreme events, sea level rise, early arrival of spring, daytime temperatures increasing, nighttime minimum temperatures increasing, and so on and so forth, to say that even though this is a short time series, this is not likely to be secular variability. The complications of Antarctica, again compared to Greenland, are obvious here. You can see that the mass loss again has a steepening slope here in the recent decade, with an acceleration compared to the previous few years here. And the ice loss here is less at 125 gigatons per year, and it's very heavily concentrated down here. I think this is the Amundsen Sea Pine Island Glacier region, and again greater losses on the edge, with some regions with higher glacier accumulation. As we said, the Antarctic circumpolar current is doing complicated things like warming the atmosphere and increasing humidity and potentially increasing snowfall over some of the regions where glacier could be accumulating mass. Okay, so just to remember that Antarctica locks in 56 meters of sea level rise, so we have to be very careful about the net loss, which is very clear here. Okay, even though there are small places which are gaining, the losses completely dominate the overall picture. If you look at all the glaciers across the world, not just Greenland and Antarctica, but all the mountain glaciers, including the Alps, the Pyrenees, mountains in the US, in Asia, in Africa, and so on, you can see that there is decade by decade increase in the mass change or loss in gigatons per year. So these are negative numbers here, and this scale is increasing this way, so the sea level equivalent in millimeters per year also is increasing. So we are at average of 1.5 millimeter per year just from the glacier contributions. Okay, we have to be careful about that, because there is also the thermospheric contribution, which is much larger, as we will see. So this time series here is much longer. So this is satellites plus lots of other data for I think there are hundreds of little glaciers across the globe, which are all accounted for here with the best data they can compile over this longer period. So there is a kind of accelerated mass loss here since about the let's say 80s, and the 70s, 60s and 70s still seem to be somewhat stable in terms of the mass loss at about 100 gigatons per year, but since then it's been accelerating, and we've seen that the warming is also accelerating. So the contributors to global sea level rise can be separated. This is still looking at the satellite period, so this is basically Topex Poseidon, and it's looking at added meltwater. So this is mostly meltwater from added water, mostly meltwater from glaciers, and this is the thermal expansion. Sorry if I said this was greater, I was wrong. So obviously there is a significant contribution of the two to the observed total sea level rise, and just over the last 2.5 decades, there's been about 10 centimeters of sea level rise. The patterns are not uniform. As we said, where the glaciers are melting, actually sea level would drop relatively, because the land that was pushed under the glacier because of the glacier weight would rebound. It's called isostatic rebound. So relatively locally sea level would drop, land rises. And when the eustatic distribution of the meltwater happens, sea level rise is actually higher away from the glaciers. We have to put that in the context of projections. Now this time series is going even longer, because tide gauge observations have been calibrated and combined with satellite data to produce long-term sea level rise anomalies. So you can see there is the baseline of 2000 at 0. Before about 2000, obviously that's 0. The sea level were lower than at 2000 by oops, why did that happen? By about that's about 10 centimeters, let's say. Okay, and it started increasing already in the 1950s and 60s along with the CO2 rise we were seeing, and it continues to rise as we saw in the satellite period up to 2020. That is now expected to go very high, up to 2.5 meters in the extreme projections, and high, intermediate, low, and low. So even the lowest one here gives us about 0.5 meter or 40 centimeters. Okay, so this is what we have to watch out for with bending the curve, where the solutions are going in terms of mitigating warming and meeting global warming targets of less than 2 degrees, and if we are lucky, maybe even 1.5 degrees. And the difference between 1.5 degrees and 2 degrees centigrade has been reported in a special report from the IPCC last year. But as we said several times, the emissions are pretty much on business as usual scenario, so the high scenario. So it's just a question of how much of the glacier mass across the world, and especially from Greenland and also from Antarctica, would be lost, and how much sea level rise would result from that. More than a meter is going to create huge problems for places like Bangladesh, many of the island states, places like Florida, Manhattan, and Gulf of Mexico, New Orleans, and so on. So the picture is not going to be very pretty if the high rates of melting occur, because we do not manage to bend the curve sufficiently in the coming decades.